All right, let's jump right in. Today, we're getting fundamental. We're talking about the very materials that build our world, from massive skyscrapers to the house you're in right now. It all comes down to the science of what holds things up.
I mean, think about it for a second. We walk through buildings every single day, but we rarely stop to consider the incredible engineering that keeps them standing strong and safe day in and day out. And that's really the heart of it. The strength, the durability, and yeah, the safety of any building. It isn't magic. It's a direct result of the materials that were chosen to build it. It's a story that starts with science, right from the ground up. So here's what we're going to break down. We'll start with the big question: what holds our world up? Then we'll dive into cement, the binding force of it all. After that, concrete, the real strength in the mix. We'll also touch on some timeless titans, bricks and timber, before tying it all together with the foundation of safety. Okay, let's get into it. Having a deep knowledge of these materials is what separates a safe, long-lasting bridge from, well, a disaster waiting to happen. Understanding how things like cement, concrete, bricks, and timber actually behave under stress, that's the absolute bedrock of modern construction. So let's start with the most essential ingredient, the literal glue that holds so much of our modern world together: cement.
The most common type you'll ever run into is called Portland cement. At its core, it's what's known as a hydraulic binder, which is just a fancy way of saying it hardens when you add water. It's made by superheating a really precise mix of clay-rich stuff, that's the argillaceous part, and lime-rich stuff, called calcareous. But here's the catch. On its own, this powerful powder sets way too fast. You couldn't possibly work with it on a construction site. So what's the secret ingredient that tames it? A mineral called gypsum. And this is exactly why gypsum is so critical. Adding it to the mix slows down or retards that initial setting process. Without it, the concrete would start to harden almost instantly. With it, workers get that crucial window of time they need to mix it, move it, and pour it exactly where it needs to go.
Okay, so if cement is this important, how do engineers make absolutely sure that every single bag is strong and safe? You can't just eyeball it, right? Quality has to be precisely engineered and measured. It all comes down to a series of really important tests. First up is the consistency test, which is all about figuring out the perfect water-to-cement ratio to get a good, workable paste. Next, the setting time test makes sure it hits that sweet spot. It gives workers at least 30 minutes to do their thing, but it has to harden within 10 hours. And finally, the strength test does exactly what it sounds like. They literally crush small mortar cubes to find their breaking point. This guarantees the material can handle the load it was designed for.
And all of these properties can be boiled down to some key numbers. Take this one, 3.15. This is the typical specific gravity of Portland cement. Just think of it as a super precise measure of its density. It might seem like just a number, but for an engineer, a figure like this is absolutely vital for calculating the exact weight and volume of materials needed for a massive project. It's all about getting the balance perfect.
So, cement is the key ingredient, the binder. But what happens when you actually mix it all together? Well, you get concrete. We've talked about the glue, so now let's talk about the final product, the single most used building material on the entire planet.
You see, concrete isn't just one thing. It's a composite, a recipe really. You take your cement, you add water, and then you mix in aggregates. That's stuff like sand for the fine aggregate and gravel or crushed stone for the coarse. And sometimes special chemical admixtures are tossed in to give it some unique properties. Now, one of the most important properties of fresh concrete is its workability. Think of it like cake batter. If it's too thick, you can't pour it into the pan. If it's too thin, it's just a runny mess. Concrete has to be just right, so it can flow perfectly into forms and around steel reinforcement without all the heavy gravel just sinking to the bottom. So we all know concrete is incredibly strong. But here's the thing, its strength isn't the same in every direction. It is an absolute champion when it comes to compressive strength, that is, resisting being squeezed. But what happens when you try to pull it apart or bend it? And this table right here reveals concrete's secret weakness. Its ability to resist being pulled apart, that's its tensile strength, is only about 10% of its massive compressive strength. That's a huge difference. And it's not much better at bending or shearing. This right here is the single biggest reason we embed steel reinforcement bars, or rebar, inside concrete. It's a perfect team. The concrete handles all the squeezing, and the steel inside handles all the pulling and bending. Okay, let's switch gears for a minute and talk about two of the OGs, the original building materials that have been with us for thousands of years, brick and timber. So, what actually makes a first-class brick? Well, it's not just about how it looks, it's all about performance. It needs a minimum crushing strength, of course, to support the weight above it, but just as important is how it handles water. It needs to absorb just the right amount of moisture, somewhere between 12 and 15%, so the mortar can form a really strong bond. If it absorbs too much water, the brick gets weak, too little, and the mortar just won't stick right. It's a really delicate balance. Now, when it comes to timber, you've basically got two main categories. You've got hardwoods, which come from deciduous trees, the ones that shed their leaves, and these tend to be denser and a lot more durable. Then you've got softwoods, which come from conifers or cone-bearing trees, and they're usually lighter and a bit easier to work with. But here's a crucial step. You can't just chop down a tree and start building with it. Freshly cut wood is full of water. Seasoning is the super important process of drying it out in a controlled way. If you skip this, the wood will shrink, twist, and warp as it dries inside your structure, which is a recipe for disaster. Seasoning is what makes sure the wood stays stable for the long haul. So, as we start to wrap up, let's bring all of these ideas back together. We've looked at the what, so now let's really focus on the why. And here it is, the big takeaway. Cement, concrete, bricks, timber, these aren't just raw materials we dig out of the ground. They are precisely engineered products. Every single batch is governed by strict standards and put through all those rigorous tests we talked about, all to guarantee it performs exactly as designed, every single time. And that is really the bottom line. True safety in construction isn't just about a clever design on a blueprint. It's about a deep, scientific understanding of the materials themselves, from their chemical makeup to their physical limits. That is the true foundation of civil engineering. Which, leaves us with a pretty interesting question to think about. As our cities grow taller and the challenges we face get bigger, what will the next generation of materials look like? What new science will define the building blocks of tomorrow's world?